Hi, I'm Steve from CellScale Biomaterials Testing. Today I'd like to show you a software tool we've developed for analyzing the data from our materials testing systems. I'll be demonstrating the software on a UniVert system, but the software tools are similar for the MicroTester and BioTester series of products. This is the CellScale UniVert. I have mounted a test sample to the low-force grips. Note the light plastic upper grips to minimize the tear load on the load cell. I'll just move over to the software screen, and you can see the loaded test protocol. I've applied a speckled contrast pattern to the specimen to allow real-time non-contact strain measurement. I've highlighted the entire surface of this sample. I will now select the middle 50% of that region as my area of interest. My protocol specifies 25% strain in this region. I could have also specified my protocol in terms of grip displacement or applied force. I have also specified a 2 Newton preload to ensure there is no slack in my sample at the start of the test. I will now execute the test. During the test, we're seeing live feedback from the force and displacement graphs on the right side of the screen, as well as live feedback from the imaging system. Moving now to the post-process software module. Initially on screen, I am looking at a displacement versus time graph. I can also show a range of other parameters on the X and Y axis of this graph. I can change the screen layout to show multiple graphs and use this slider to move through the test and show the data values and corresponding image at any point in time. For more complex test protocols involving multiple cycles or sets of cycles, we can use the filters to show only some of the test data. Let's calculate a Young's modulus for this test by using a linear elastic material model. To do that, we will need to calculate stress using the measured forces and the specimen cross-section information. In this case, it is a square cross-section, 12 millimeters wide by 1 millimeter thick. It has a starting gauge length of 40 millimeters, although I will actually be using the strains measured directly during the test rather than relying on the grip motions. To calculate the modulus, I need to add a curve fit to the stress-strain data. I'm going to select a start point of 10% strain and an end point of 25%. I can do this by clicking on the graph or typing values in the appropriate fields. Once I click the Finish button, I can see a set of calculated values including maximum load, maximum stress, maximum strain, break detection, maximum elongation, ultimate strength, and modulus of elasticity. In this case, the modulus is 2.21 megapascals. I can also go back to the main screen and see the line plotted along with the data and equation for the curve fit. I can compare this result with 2 identical test samples I ran earlier by selecting Compare Tests. Let's now look at the image analysis module. We calculated the strains in real time, but in some cases it is useful to measure the strain patterns in more detail. In this case, I am superimposing a virtual grid on the surface of this sample in its unstretched state. The contrast speckle pattern allows our software to track motions on the surface of the specimen while it is being deformed during the test. As I cycle through the test images, I can see the displacements of each grid point or their motion paths. I can also measure and visualize the regional strains. That's it for our demonstration today. I hope you found it informative. You can find out more on our website at www.cellscale.com, and you can email us at info@cellscale.com. We'd love to chat about your research projects and answer your questions on any of CellScale's technologies.